Hey, welcome! Have you ever looked at a physics textbook and felt like you were trying to read a completely different language? Well, guess what? You're not wrong. But the good news is, just like any language, it's got a basic alphabet and a set of grammar rules. And today, we're going to get fluent.
I mean, take a look at this equation. Looks pretty intimidating, right? It's the formula for thermal conductivity. But what if I told you this whole thing is built from the exact same 7 fundamental letters as something super simple, like the speed of a car? Yeah, that's the secret we're unlocking today. You see, the universe has a language, and it's called physics. And if we want to understand its rules, everything from why an apple falls to how a galaxy spins, we first have to learn the basics. We have to learn its language.
So, where do you start with any new language? Well, you start with the alphabet, of course. These are the absolute most basic building blocks that everything, and I mean everything, is built on. First up is the idea of a unit. A unit is just a label. It's the word we stick on the end of a number so that it actually means something. I mean, saying a box weighs 10 tells you nothing, but saying it weighs 10 kilograms, now we're talking. Now it has meaning.
And here they are. These are the 7 and only 7 letters in the entire alphabet of physics. These are the fundamental units. We've got the meter for length, the kilogram for mass, the second for time, and a few others. And here's the really crucial part. They're all totally independent. You can't describe a kilogram using meters or a second using kelvins. They are the absolute bedrock of all measurement.
Okay, so we've got our 7 letters. Now, the real fun starts. It's time to combine them to make some words. In physics, we call these derived units. Let's see how it works.
A derived unit is exactly what it sounds like. It's a new unit that's derived from our fundamental ones. Almost all the things we measure in daily life, like speed or force or pressure, they're all derived units. They're the words and sentences of physics.
So let's build our very first word. And we'll start with something we all know, speed. There's no single fundamental unit for speed, right? So we have to build it ourselves.
And check out how simple this is. We just start with the formula we all learned in school. Speed is distance divided by time. Then we just swap in the fundamental units. The unit for distance, that's meters. The unit for time, seconds. And there you have it. The derived unit for speed is meters per second. Easy, right?
All right, let's level up. How about a slightly trickier word, like force? We're going to use the exact same logic.
Now this is where it gets really cool, because you can see how the language builds on itself. Force is mass times acceleration. Okay. The fundamental unit for mass is the kilogram. We know that. But what about acceleration? Well, acceleration is already a derived unit. It's the change in speed, meters per second, over time per second. So that's meters per second squared. We just plug that in, and boom. The derived unit for force is the kilogram meter per second squared. It's just so elegant.
So we have our letters, the fundamental units, and we can build words, the derived units. But how do we know which combinations actually make sense? What are the rules? Well, that brings us to the grammar of physics, dimensions.
Seriously, think about it for a second. Why can you add 5 feet to 10 feet, but you can't add 5 feet to 10 kilograms? It feels obvious, right? But there's a deep, fundamental rule behind it, and that rule is all about dimensions.
So here's the big idea. A dimension isn't the specific unit you're using, it's the type of thing you're measuring. For example, a meter and a mile are totally different units, but they both measure the exact same dimension, length. And it turns out pretty much every physical quantity can be described as some combination of just mass, which we call m, length, L, and time, T.
Let's just make this crystal clear. On the left, you have units, the specific way we measure something, like a meter or a kilogram. On the right, you have the dimension, the fundamental idea behind the measurement. So meters, feet, light years, they're all just units for the single dimension of length, L. A pound, a gram, a kilogram, all units for the dimension of mass, m. The dimension is the concept. The unit is just the ruler we choose to measure it with.
Okay, let's circle back to our force example. Remember, its unit was kilogram meter per second squared. Now we can translate that into its dimensional grammar. The kilogram represents mass, m. The meter represents length, L. And per second squared represents time to the power of -2, t to the -2. So the true fundamental identity of force, its dimensional formula, is ml t to the -2. No matter what units you're using, this is what force is.
All right, I know what you're thinking. This is kind of neat, but what's the point? Well, the point is that understanding dimensions gives you actual superpowers. Seriously, it gives you a toolkit for checking, converting, and even predicting the laws of physics.
When you master this, you unlock 3 incredible abilities. First, you can look at almost any physics equation and instantly know if it's wrong. Second, converting between different units becomes a piece of cake. And third, and this is the most amazing one, you can actually derive new physical formulas, basically from scratch.
Let's look at that first superpower. There's a rule called the principle of homogeneity, which is really just a fancy way of saying both sides of an equation have to be talking about the same stuff. You can't have an equation where the left side is in kilograms and the right side is in seconds. It's like saying 5 apples equals 2 oranges. It just doesn't make sense. As you can see with this classic motion equation, when we check the dimensions of every single term, they all work out to be length squared divided by time squared. So it passes the check. It's dimensionally consistent.
And now for the main event. This is the one that honestly feels like a magic trick. We can use what we know about dimensions to build a formula without even doing an experiment.
Let's say we want to figure out the formula for centripetal force. That's the force that keeps something moving in a circle, like the Earth around the Sun. We can make a pretty good guess that this force probably depends on the object's mass, how fast it's going, and the radius of its orbit. But how do those pieces fit together?
We don't have to guess, we just use dimensional grammar. First, we set up a relationship where force is proportional to mass, velocity, and radius, each raised to some mystery power, A, B, and C. Then we just replace each quantity with its dimensional formula. And now, look, it's just a puzzle. All we have to do is make sure the powers of mass, length, and time match on both sides of the equation. We solve for A, B, and C, and we find that A is 1, B is 2, and C is -1. And just like that, the formula just appears. Force is proportional to mass times velocity squared divided by the radius. That is just incredible.
So here's the big takeaway. Learning about units and dimensions isn't just about memorizing stuff for a test. It's about understanding the deep structure of the physical world. It gives you the power to check, convert, and even predict the laws of physics for yourself. You now have the key to a secret language. The language the universe is written in. You know its alphabet, you can make words, and you understand its grammar. It really makes you wonder, doesn't it? With this tool in your hand, what other laws of the universe are just out there, waiting for someone like you to decode them? Thanks for watching.